So this lecture is about the CDF function, or the cumulative distribution function. The setup is that we have a random variable x. That means that in the background there is an experiment, there is a sample space S, and x is a function from S to R. We know that the collection capital X less than equal to lowercase x, that is an event. Which event it is depends on the value of lowercase x. Since this is an event, we can figure out its probability, which we denote like this. So this part, an event, that is a subset of the sample space S, while this part is a number which is between 0 and 1. Both of these depend on the lowercase x, which is a real number. So what we do is we simply define this probability as a function, which is then typically denoted by capital F as a function of lowercase x. So this is just simply shorthand notation to save us from writing so many symbols. The important point here is that f becomes a standard function mapping a real number, lowercase x, into a number that must be between 0 and 1, since it's a probability. So capital F has this property as a function. So exactly how this capital F function maps real numbers into 0, 1, well, that will depend on a lot of things. It will depend on how the random variable x is defined, but it will also depend on the experiment and the sample space and the probability measure. So to see this, let's consider a very simple example where my sample space just consists of alpha and beta. My probability measure is defined as the probability that alpha will be the outcome of the experiment is, let's say, 0.7, and the probability that beta will be the outcome is 0.3. On top of this, I define my random variable, and let's just say it maps alpha into 0 and it maps beta into 1. So this is an example, and I can illustrate this example using a simple picture like this. So alpha and beta are the only elements in my sample space. X will map this into 0 and this into 1. So if we consider this event, x less than equal to x, this event will become the entire sample space if lowercase x is greater than or equal to 1. Both alpha and beta are mapped into a number less than equal to 1. It will become the event consisting of only alpha if x is greater than equal to 0 but strictly less than 1. And it will become the empty set if x is less than 0. So in this example, the CDF function f of x, which again is defined as probability x less than equal to x, will then become equal to, well, the probability of the entire sample space is 1 if x is greater than equal to 1. The probability of alpha was 0.7 if x is between 0 and less than 1, and it becomes 0 if x is less than 0. So if you want to plot the CDF function for this particular example, it would look something like this. When x is less than 0, it's 0, so it goes like this. It jumps to 0.7 when x becomes equal to 0. So if this is 1, then maybe 0.7 is right here. So it's equal to 0.7 when x is 0. And we draw that using a closed circle and an open circle. So there is a jump in the function from 0 to 0.7 at x equal to 0. Then it is equal to 0.7 all the way until we get to the number 1, when there is an additional jump, in this case up to 1. When x is equal to 1, f of x is equal to 1, and then it stays at 1. So this is the graph of the CDF function f of x for this particular example. So the CDF function will have a couple of properties which are always satisfied no matter what the sample space is, no matter what the probability measure is, and no matter how the random variable is defined. The first of these properties is that f must be an increasing function in x. So remember, that means the following. If I have x here and f of x here, and I look at the function at two different values, a and b, where b is greater than a, then whatever value it takes at a, f of a, it must take a value that is at least as big as f of a in b. So if it takes the value f of b here. So these 2 points are on the graph of f. So f of b must be at least as big as f of a. We can see in the example that we just considered that we do indeed get an increasing function. It's not hard to realize why that must be the case. It's simply because of the definition. This simply says that the probability that x is less than equal to b must be greater than equal to the probability that x is less than equal to a. And that must be true if b is a number that's greater than a, if p is to be a valid probability measure. The second thing we can see is that f of x is always between 0 and 1. It cannot be greater than 1, it cannot be less than 0. That too is not too hard to understand, and that's simply because the CDF function is a probability, so it must lie between 0 and 1. The third one says that when x goes to infinity, then f of x must go to 1. We can write this in the following way. The probability that x is less than equal to x must go to 1 as x goes to infinity. And if you think about that, if you put in here a very, very large number, then the probability that x will take a number less than equal to that must eventually converge to 1. On the other side, the limit when x goes to minus infinity must be 0. And again, that just says this must converge to 0 as x goes to minus infinity. When lowercase x converges to minus infinity, then the event x less than equal to x contains hardly no outcome, so this probability must converge to 0. Again, we can see that our example does satisfy property 3 and 4. It converges to 1 when x goes to infinity, and it converges to 0 when x goes to minus infinity.